Hi, my name is Tom Manning, and I'm a professor of chemistry at Valdosta State University. We've been doing work in the Gulf of Mexico for the past 16 years now with biofilms and growing different types of marine creatures. We'd like to talk to you a little bit about how we can extend this technology to doing some work along the coast of Georgia with oysters. Typically, people think of oysters and they think of food, but oysters play a tremendous role in preventing coastline erosion, and they also help with water quality. An example is a single oyster can filter up to 50 gallons of water per day. Coastal erosion, a great example is the coast of Louisiana, where they lose land every day because of oyster beds that have disappeared and there's nothing but muck there. Our technology is based on cellulose, which you can see some soaking in a runway at the Florida State University Marine Lab. We like to grow biofilms on things, and this is great for capturing wild diploid oyster spat. For the past 15 years, we've produced a number of new cancer drugs and antibiotics that have entered preclinical trials by growing bacterial mats on different surfaces. By varying the surface and varying the chemistry of the surface, we can vary what type of bacteria we grow in the ocean. But along the way, what we found is that all sorts of other things like to grow on these surfaces, including everything from barnacles and oysters to coral stubs to different types of sessile invertebrates. There are literally trillions of species of marine bacteria in the oceans. So how you grow or what you grow is a function of the chemistry. What we have found is that by varying different chemical parameters, we can grow different types of films. In the upper left, you see a bacterial film that is nice and thick, and you can see where we captured it on the right. These films are important for things such as oyster spat, coral larvae, sponges. What the bacterial covering is of a surface will impact what's actually growing there. So that's what our focus has been and is currently on oysters, trying to grow wild diploid oysters on green, economical surfaces. This past summer, we received a grant from the National Science Foundation to have our technology for growing marine life tested for commercialization potential. 24 teams from around the country received these grants in our cohort that was held in Washington, D.C., and we were one of 6 that were given thumbs up for commercialization. We have 3 patents pending based on this technology, and they're focused on using small modular reefs to grow things as opposed to single large structures like ships or planes. We use nutrient-enriched cellulose. Cellulose is biodegradable, and by what we soak into it, we can predict what we're going to grow. And then we also have a concept called biodegradable concrete, where we mix a host of organic and inorganic nutrients in with concrete. So not only do things grow on it much faster and in a more predictable fashion, but also with time, these structures will degrade and go away, leaving behind a living ecosystem. With our treated wood and treated concrete approach, we've been able to show that you can grow oysters, wild diploids up to greater than 3 inches in 12 to 13 months. This is in the northern Gulf of Mexico. Location is obviously critical. The chemistry of the surface is critical, but also the geometry of the surface is critical. And you can see both on the left and on the right, these particular ones, the one on the left was grown in an environment where there were also lots of competition from barnacles. And on the right, you can see the large colony that grew on a piece of wood in a little over a year. There are many geometries or combinations of cellulose and concrete that you can come up with, but they're going to be dictated by local currents, what the bottom is composed of, how far you have to lift your substrate off to avoid muck. Is it in a tidal area or a high tide, low tide area? And do you want to retrieve and move it? A simple example of how our system might work is near an existing oyster bar. It can be very small because they put out lots of spat. We put our structures. They become colonized over a period of maybe a few months, starting in April or May and being moved in August. and then you can deploy to another area and start a whole new oyster bar. The advantage to our systems is that they're small and modular, which means they can be moved. They adhere to the principles of green technology, which means that they're sustainable and they will not leave behind anything that's permanent. They're biodegradable, and typically if you get the chemistry of the surface right and you put it in the right place, you can predictably grow something like oysters. Our project, which has been led by a team of students, has received some national press, international, in Sport Diver Magazine and Green Technology Business Review. At that point, we were focused on growing corals, but we found that there's more opportunity with oysters. We are currently in the process of filling out a permit to do some work, hopefully around Jekyll Island and maybe some other areas in South Georgia. We are more than willing to collaborate with people. We do have a permit now for the state of Florida for 6 locations in Apalachicola Bay, and we're timing our work there with the increase in water temperature and the release of the spat. Thank you very much, and we appreciate your time and effort.